Okay, so any question from this time? Today we'll finish our brief introduction of classical computation. So let's do a quick review. So last time the most important thing about this chapter is you need to remember these big O notations. There are 5 of them. So basically, this big O means smaller or equal to, small O means smaller, and big omega means greater or equal to, and small omega means greater, and there is this big theta means equal to, roughly. And the small O and the small omega you don't see that much, but big O means gives you a way to say upper bound of f, and the big omega give you a lower bound of f, and the big theta give you a good characterization of f. Okay. So those you need to remember. And then switch to this slide. And then we start to talk about computational complexity. So in computational complexity, we study how much resource we need to solve a computational problem asymptotically. And last time we already covered what's a computational problem. So in this very theoretical formulation, we think a problem as a language, this formal language, and mathematically, a formal language is a subset of this set of string of any length. So it's a subset of all strings. And so mathematically this seems weird, but really it's just a way to write down the truth table of a Boolean function. So a Boolean function of all size. And here we give a very easy example of a language. Here is the language of every string that doesn't contain 1. So 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, etc. And this will correspond to the Boolean function where the output is 1 when your input has all zeros. Okay. And as we said, the language is really correspond to a Boolean function or a decision problem. That is, you are given an input, you want to compute the 0 or the 1, and the output is 1 if your input is inside this language, and the output is 0 if your input is not inside the language. Okay. So that's a very obvious correspondence. So you get a decision problem or a Boolean function. I guess, sorry. So it's a little bit different. So decision problem also doesn't have a size, doesn't have a fixed size. So this x can be any size. Function, I guess the function also can have this. But when we talk about function, usually we have a fixed input size. Anyway, so we see here that for any, if you give me a language, then there's a very natural associated decision problem like this. And this is like computing a Boolean function. And here we have a bit more complicated language that will encode the primality testing problem. So the language will include every prime number. And so this language is corresponding to testing whether your input is a prime number or not. And so if you give you an input, and you want to say this input is inside language. Oh yeah. Okay. And the two resources people in theoretical computer science think most about time and space. And time is pretty obvious. That's how long it takes your program to run to give you whatever answer you want to seek. And space is a bit more physical. This is how much RAM your computer must have to run the program you want to run. But I guess we'll actually focus on, wait, let me look, do I have, okay, I forgot to have that. But anyway, yeah, today's, so the following things will actually focus on, mostly on time. Okay. Although, yeah. Although later in the course we'll talk a little about the space. Okay. And so when you think about time, the most obvious complexity class we define is this P, that's polynomial time. That's the set of problems, or in terms of our notation, a set of languages that can be solved in polynomial time. And here, so this big P is a set of language that's solvable in time order n to the k. So this is a polynomial, and they want some constant k. And here n is the size of the input. And in practice, these P class are usually pretty solvable in our computers. Although you can make very theoretical counterexample where this k is like 1000, then it's not very practical. But usually when we consider natural problems, and when you get the polynomial time algorithm, sometimes it also have k to the 1000, but people usually are able to optimize it to reasonable k, like 2 or 3. And we can do this polynomial time problem. And this P is really nice because different computational models usually can be converted to each other by a polynomial time overhead. And that means P in different models really are the same set. So for example, the Turing machine and the second model, they have the same class of P. So it's really nice. And so this is really the basis of modern computer science, is deciding whether things are in P or not. So things can be efficiently computable or not. I think this is the most important thing in modern computer science. And I remember in ancient computer science, people are trying to decide whether things are decidable or not. But really, when people actually start building computers, right, so decidable. Yes, build this. Great. Anyway, so in ancient time, people don't have a computer, so they thought the computer can solve everything very fast. So they just want to see whether things are decidable or not. But when people actually start building computer, they find out some problem, even for computers, it took significant time to solve. So really, we want to see the problem is in P or not. And this is the main focus of modern time computer science. So that's a review. Any question before we go into NP? Okay, then we go into the next complexity class. Oh, sorry, we skipped this. And so the thing that computer science do is study complexity class, as we already see an example in P. So complexity class is a set of language that are about as hard as each other, and we'll give more motivation of this thing later. And a very famous complexity class that you guys probably all heard of is this NP. And this N stands for non-deterministic. So this is non-deterministic polynomial type. And the important thing to remember is this N doesn't stand for not, but it stands for non-deterministic, and we will not go into the detail of why it's called non-deterministic. Anyway, this is NP. So informally, NP is a set of language that can be efficiently verified. And why is this important? Is because, because we encounter this kind of problem a lot in practice, as we will see later. So when people start to do computers and try to write algorithms, obviously not everything can be done in P. But they find out there are things that can be done. so things that we don't know how to find the answer very quickly, but if we do find the answer, we can verify the answer is correct very fast. So formally, the NP is defined this way. So the language is the NP if there is a polynomial time Turing machine, so basically a very efficient algorithm M, such that if you have a yes instance, so if your input is in the yes preimage, then there is this weird witness thing. This witness can depend on your input. So then this checking algorithm. Yeah, so remember we have this very efficient checking algorithm. So the checking algorithm will look at your input and look at the witness and say, okay, yes, this input is good. And when the other way around, if the input is not an instance, so the input is a non-instance, then then for all, so this is for all. If we use this, but anyway, let's say write this down. This is for all. So for all witness string W, this verifying algorithm will reject. Yeah. So this verifying algorithm only have one bit output. So only say accept or reject. And so we can think of this in some kind of interaction model. And so when you have an NP problem, that means someone can, and let's say you want to solve an X instance, and so there is a verifier and there is a prover, and the prover is very powerful, and if X is in L, then the prover can prove to the verifier that X is entering L because the prover can send the witness to the verifier, and the verifier can check that can compute this M because this M is very efficient. So the verifier can compute this N of X omega, N of XW, and see that it's actually correct. But when X is not in the language, then the prover cannot trick the verifier to accept because all the string W will not make the verifier accept. Okay. So this is kind of an interaction model. Prover, verifier. Okay. And So anyway, so some things about these NP class. Well, obviously this N is something that lets you verify whether X is yes in sense. So whether X is in your language L. And an important part here is that the yes and the no instance of this language is not symmetric. So by this we mean that here you cannot just swap this in L and not in L. So if X is in L, then there exists a winning string to let you say verify that X is in L. But when X is not in L, there is not this, don't have this verifier string to let you verify X is not in L. And yeah, so X in L and X in not in L are not symmetric. And obviously you can switch this in to not in and this not in to in, and you will get another complexity class where you can verify X is not in L, tells you whether X is in L or not. Then maybe we'll just search through all the W to see. So given X, we can just search over all the W to see whether there is some W that is accepted. And the trick point is that the possible number of W might be really big. So if we want to search through all the W, it can be very hard. So NP is not obviously in EP. And here we have an example that we probably should say earlier. So very easy example of a problem in NP is this factoring. And so this factoring problem is that we are giving a number and we want to see whether it is so this is a little harder than primality testing. So we are given a prime number and we want to find its factors. So we want to say whether it can be written as multiplication of two non-trivial factors. So both of those are not 1. And in short, you want to see, so input is this number m, and we want to factor in is input is m, and we want to see whether n equal to some p times q, and p and q both non-trivial. But here the formulation is a bit trickier because we keep talking about decision problem, and the factoring is it's not really a decision. You want to output a p or a q. And the decision problem only output 1 bit. So we use this weird trick to make it into a decision problem. So instead of just input have n, we also have this threshold L. Okay? So L is some number that's smaller than n. And the decision, so both of them are integer. And now the decision is that we want to see whether there is a factor of n that's smaller than L. So basically, this factor of n, you think of like p. So basically, we're asking whether p is less than L. And you can see that this decision problem and the original search version for factoring are really equivalent. Because let's say if m can be factored into some pq, and you want to find p, and then you can solve this decision version, then you can just move your L around and do a binary search. Then you can find this p in like polylog time. And the other way around, obviously, if you can factor m, then you can get this p, and you can just check whether p is less than L. Okay, yeah, want to see whether p is less than L. So basically, you want to see whether p less than L here. So we give a very first prove that the decision version are really equivalent to the original computation version. And anyway, so back to our NP. So what is this factoring in NP? Well, now the witness is just this P, right? So if someone really smart told you that this big number n can be written as a multiplication of P and Q, and so the prover just told you this P, then you can check that. Well, you can divide your n by P and find out that P is actually a factor of n, and so you can do the division. So now the W equal to P. So you can check the division to find out that P is actually a factor of m, and obviously you can check the how big is P. So P is actually less than L. So if you are in the yes instance of M and L, you can and someone told you this P, then you can easily check that well the P actually satisfies those two conditions. But now the point is this is not in P, because if you didn't have someone told you what this P is, and then you want to find this, then you need to basically do brute force search, and that take actually there are smart algorithm, but that's they were kind of dumb. So if you do brute force search, then it takes a lot of time to find this P. So this might take you like exponential time, exponential in the length of this integer. Okay. Yeah. And okay, then there is a little digression note. That is, why do we want the really weird decision version like this? So why don't we just test whether m is a prime number or not? And it turns out testing whether some number is a prime number is actually in P. So on the decision version of factoring, we need to do this weird ML stuff. And anyway, back to the actual important part. So this is the example of things in NP. So a lot of computation problems have this kind of property where if you have an instance, if you get a yes instance, then someone can prove that you are actually in a yes instance with some short witness, and you can check that. So you can check the answer really fast, but it's hard to find the answer. Okay. This is kind of like, I don't know, writing your homework or writing a theoretical proof. So there's some theorem, and want to say the theorem is correct, then someone write a proof. Usually it's easy to see the proof, to check the proof. But if you want to come up with a proof yourself, it's very hard. Okay, so that's some weird real world example of this. But anyway, we are a bit too slow. Okay. Yeah, so that's NP. Any questions? Okay. So yeah. So now we start to talk about the complexity class, relation between complexity class. And these are kind of what complexity theories do. So obviously P is in NP. So here we study the relationship between P and NP. So obviously P is in NP because, well, you want to see whether P problem you can find this kind of formulation, well, then you can actually don't need any witness because the problem is easily solvable. So the witness is nothing, and the verifier is you can run your P algorithm that efficiently solve your algorithm, and you just check whether it instance yes and no. Okay. And now, remember those are all set. Now the problem is there a separation between P and NP? Okay. And this is the big computer science problem, and the answer is we don't know. Okay. So it seems like NP, well, it feels like NP should be harder than P, but we don't have a proof yet, rigorous proof yet, that they are different. And maybe it's also possible that there are some very smart algorithms that just show you that everything NP is actually in P. And here we have the first example of our complexity class graph. So this is what complexity series like to do a lot, because you will see this kind of thing happen a lot. So we'll define a lot of different complexity class, but it's actually very hard to prove the exact relation between each of them. So we'll just draw a picture about what we know about them. Okay. So we think that NP is bigger than P, and there might or might not be some separation between them. It's empty space. Okay. And then remember there is another there is another class that we talk about that is called NP. Basically flip the yes and no on NP, and it's a quadrant of where co-NP equal to NP, and the answer is also we don't know. So if we draw all three of them, we have the NP, there is a co-NP, and there is an interaction between NP and the co-NP, but where that's also exactly equal to P, we also don't know. Okay, so that's complexity class picture. And then we have 10 minutes. Okay, we can probably finish this. But any question about this complexity class picture? Yeah. Well, as we know more class, we'll have more complicated mental picture about the inclusion, these Venn diagrams between different complexity classes. So this is kind of funny because so all these whether classes are equal to each other are too hard. So what we do is we draw a picture of what we know about them. Anyway, so let's switch to this reduction. And reduction is a very useful technique, both practically or theoretically. So in theoretical terms, we have two different languages, A and B. So they are encoding different problems. And we say A reduces to B, means that we can solve A if we can solve B. And usually that means that we can have some polynomial time overhead, because we think everything in P is cheap. And in terms of algorithm, this means like if we have an algorithm that solves the problem in A, then the algorithm solves the problem A, then we can have this algorithm pretty efficiently. So we won't have polynomial number of lines. And but there is an algorithm in B as a sub-algorithm inside this algorithm. Okay. So we'll call this algorithm for B inside this algorithm for A. And if this small block runs really fast, and you only have other things like in polynomial time, and this will be pretty fast. And in terms of which problem is harder, we'll will feel that problem B is harder because solving it is harder. So this algorithm is more powerful, and so we call this more powerful algorithm to solve your easier problem. Okay. And then there is a small distinction between type of reduction, although and so you might see them if you read really theoretical paper. Sometimes there is a small distinction. So there is couple reduction and Cook reduction. Both of them are names for computer scientists. So couple reduction is a more direct reduction between problems. So it's exact correspondence between problems. So it says there is an efficient function, some kind of transformation f, such that you can transform an instance in A into an instance of B efficiently. So some instance in A, some instance is in A if only if you do this transformation and A is in B. Okay. And then from here you can see how this algorithm works. So here, if you have this kind of reduction, then this algorithm for A is very easy. You take the x as input, and you just compute f of x, and you throw f of x inside algorithm B, and you see answer is yes or no. Right? That's easy. But then there is also this Cook reduction, and this is not less like a reduction of problem, more like a reduction in algorithm. So it means that when you call this algorithm for B, then you can do it smarter. So yeah, you can call an algorithm for B like many times here, and even on different input. So you see that for this couple reduction, you only need to call this algorithm for B once. You only need to compute this f of x. But for Cook reduction, then you are actually using the full power of calling this algorithm B, and you might call polynomial many times. And so that's a slight difference. This is a more computational reduction, and this is more transformational problems. And obviously, this is a stricter restriction, and sometimes you want that. But anyway, and obviously, reduction is a very useful technique to write algorithms. So you will want to write sub-algorithm. But in terms of theory, reduction let us characterize our complex class better. So we can define the complete problems now. And the complete problems are the hardest problem of the class intuitively. And so intuitively is this, and more formally, we say a language L, so some kind of problem, is completed for some class A if first is inside A, okay, and second that any problems in A can be reduced to L. So if you can solve L, remember this means that, excuse me. So this means that if you can solve L, then you can solve any problem in A by coding, yeah, and let's scroll up. So kind of if you have an algorithm for L here, then you can have algorithm for L, then you can write the algorithm for any L prime by doing this coding, and that will solve efficiently. Okay. Yeah. And a term of this, more succinct term, is that we say L is A complete. Okay. and this condition, this one alone, is called A hard. So if you can solve anything in A by solving this L problem, then this L problem is called A hard. And why we would want to do this? Because we want to talk about NP complete. This you probably also heard about. And but firstly, there is a easier example that is P complete. So obviously everything in P is P complete because, this is trivial. So obviously everything in P is in P, and when you do this reduction, you don't need to do reduction because when we do this reduction, we allow polynomial time overhead. So you can just use the polynomial time overhead to solve your problem, and you don't need to actually call this subalgorithm. So that's a trivial example, but more useful example are those NP complete problems. So there are actually NP complete problems, and we won't. We don't talk about their details, but for example, there are recurring. We have extra time. Okay, sorry. So we can probably talk about recurring. So for example, 3 recurring and the 3 set. So 3 set is the most famous NP complete problem. But it's a little annoying to write down. So actually you have time, right? So we'll do this. So this is a really famous theorem that 3 set is NP complete. Obviously we don't have time to do the proof here, but so 3 set, so we have time. So 3 set is like, so this set stands for satisfiability, and you really take an input string, so we think the input as like x1, x2, x3, xn. Let's see if I can do this correct. And set. So want to see where things are satisfied, and so there are clauses. So 3 set clause. This 3 means we take 3 literal. So clause is like we take. So we think there are like an input point, and we'll pick 3 of them. So like xi or xj or sk. So for some I, j, k, e, n, okay, and you can have some negation here. So clause look like something like this. So obviously this is a logical expression. So we want to see whether there is a 1 in these 3 things, and there might be some negation. So and so this is 3 set because each clause has 3 literals here. And the 3 set problem is that so I guess the inputs there are this number and the clauses. You need to describe your clauses, and you will have a whole bunch of clauses. So you want to see like xi1, xj1, xk1, and so there are or between the literals inside clause, and you want to end through all of them, and xi2, xj2, xk2, and etc. And so this is some logical expression. You can calculate the AND/OR between all those literals, and they want to see this equal to 0 or 1. Okay. So that's a problem. And it's satisfiability, because basically you want to see whether this logical expression is satisfied or not. And this is in NP because oh sorry, I always mix this up. Okay, because this x is not input, but x is basically witness. So the input are this called structure, and this is satisfiability. So we want to see. So there is this instance that this very large logical expression, and the question is exists x such that this expression equal to 1 or not. Okay. So if there exists x that satisfy, you do all those calls and they end 10 and they are all satisfied, right? Then it's a yes instance, and if not, then it's a no instance. Okay, that's a little confusing, and anyway, and this is in NP because if this expression is satisfiable, then this x is x equal to your w. So you will give a satisfying string, and someone can check that the string satisfies all those calls very fast. So that's correct. That's in NP, and then there's a cool proof that actually anything NP can be reduced to 3 set, because you are able to think about what your checking algorithm, the n of x w do, and translate that into a 3 set. Okay. And so 3 set is in NP, and it's actually NP hard, and that's I guess the first big proof of modern computer science. That is, well, we cannot quite give you an efficient algorithm in NP, but we told you that if you can solve this problem, then you can solve anything in NP. And a lot of things in modern complexity theory is doing things like this. We try to map problem between each other. So we want to say this problem is hard and the other problem is hard, and we try to prove that they are as hard as each other. Okay, so we cannot give you an efficient algorithm for them, but at least we can say how hard they are. And we still have time, so maybe we can also do 3 color here very fast. 3 color. Okay, so 3 coloring is easier to describe. So the instance is the graph, and it's also nice because we can talk about this a little more later. So a graph in computer science are collection of vertices and edges. Okay. Graph means things like this. So maybe there is another edge here. So graph is a set of V vertices, and the edges connect the vertices. And the edge might have direction, but for now we say they have no direction. Okay. So here we have a graph that has 5 vertices, so 1, 2, 3, 4, 5, and how many edges? 1, 2, 3, 4, 5, 6 edges. Okay. So graph is just a set of vertices, and each edge will connect to vertex. Okay. So that's what computer scientists think about graph. And 3 coloring just says that we'll give you a graph like this. Then can you color, I think, the vertex? Can you color the vertex with RGB? So let's say this is R, and this is G, and this is B. And this is R, this is also B. Can you color them with, say, RGB, such that every edge has different color on its 2 sides? So obviously this one is doable because I just give you example. Oh, actually no, I do this wrong, right? So this is a bad assignment because we will have this edge that has B on both sides. So that's not good. Yeah. So we should have a G here, right? So that's a correct assignment. And but we have extra edge here, I think then it's not possible, right? But if we have an extra edge here, then it's not possible because we have 4 vertices that connect to each other. So you need 4 color to actually color those 4 edge. Yeah. Sorry, to color these 4 vertices. So yeah, so given a graph and you want to find out whether there is a 3 color of the graph. And obviously this is NP because you see the graph. Then and some witness is just an assignment of the colors. Yeah, the witness is just an assignment of a color. Then so basically the V and the E. So the number of E here is your scaling parameter n, and E is at most n squared. So at most you can check in n squared time that the assignment is correct. You just check every edge and see where the color are different. But if you want to brute force search through all possible coloring, then that takes 2 to the n time because actually 3 to the n time because that's the maximum number of coloring. And there is a reduction from 3 coloring. There is a reduction from 3 sets to 3 coloring. So this is also NP complete because if you can solve 3 coloring, you can solve 3 sets, and if you can solve 3 sets, you can solve everything in NP. So yeah, that's a quick taste of what complexity theory look like and the NP completeness. So any question? Otherwise we are exactly on time. Okay, then we can stop today. And next time we'll start talking about quantum circuits. This will be the end of classical computation. Okay, so see you on Thursday.